Okay, so we need to start chapter 6. Chapter 6 is about the electronic structure of atoms. So basically, way back in chapter 1, chapter 2, somewhere in there, so chapter 2, I think, we talked about how there's a nucleus to an atom, and then there's electrons flying around the outside. Okay, this is nowhere near enough detail to explain what is going on. Okay, but before we get even too far into this concept, we need to address the fact that electrons are very, very, very light. They have almost no mass at all, and they move at very, very near the speed of light, which means most of the time when we talk about electrons, we need to deal with the fact that they kind of behave like light. So we need a little bit of physics background, not a whole lot here, but a little bit talking about how light works. Okay, so essentially the way this works is electrons and light, all of these things, travel in the form of waves. Hoping my pen holds out here. Okay, so basically light travels as a wave, so it oscillates as it moves. It's actually part of the electromagnetic spectrum, so it actually has an electrical wave and a magnetic wave perpendicular to that. We're going to ignore the magnetic part. Okay, a few things to define though. Okay, the distance between two peaks, okay, is called wavelength, and it's abbreviated as a lambda. It's a lowercase Greek L. We're going to start seeing a lot of Greek letters, sorry. So this is wavelength. So wavelength is the distance between two peaks, or the distance between two valleys, or distance between a third of the way down and a third of the way down. It doesn't really matter where you pick. Most people pick the peaks because it's easiest to see them. Okay. The units on this are going to be some sort of distance units, so some variation of meters, might be centimeters, nanometers, who knows. Okay. That is one of the things we care about. The other one we care about is something called frequency, which is labeled as a nu. It's like a weird little curvy V. It's actually a lowercase Greek n, but it is what it is. Frequency is more if you're like in a standing position, if your light is hitting something, okay, or if it's passing by something, how often does the peak of a wave go by? How frequently does it occur? Okay, so it's how many peaks per unit of time, or how many oscillations per unit of time. So the typical units are inverse seconds. I typically write it like this. This is s raised to the -1. This is the same thing as saying 1 over seconds. I write it like this because it's easier, but it means this. For any of you physics people, this also refers to something called hertz. Hertz is basically how many oscillations per second. Okay. So there is a third value that we're going to basically ignore, is amplitude. It's basically how tall the peaks are. It doesn't really affect most of the things we do, so we're going to ignore it. If you're a physics person, it's totally, absolutely important. It just doesn't affect what we do in this chapter, so I'm going to ignore its existence. So these two things are related. The more frequently, because light travels at a constant speed, the more frequently the waves are coming by, that means that they have to be closer together. And the farther the waves are apart, the less frequently they're going to be. So they're kind of inversely proportional. And it turns out that frequency times wavelength equals c. And c is the speed of light. So the speed of light in a vacuum is 2.9979 times 10 to the 8th meters per second. Sometimes you see it as written as 3.00. I just don't want you to limit your sig figs. So keep enough sig figs to not limit your answer. So 2.998, 3.00, something like that. Okay. So basically, if you know the wavelength of a wave of light, I guess, a beam of light, you could figure out the frequency. If you know the frequency, you can figure out the wavelength. Let's do an example just so you make sure you've got one in your notes. So we want to calculate frequency of an X-ray at a wavelength of 8.21 nanometers. A nanometer is 10 to the 9th nanometers equals a meter. So it's really, really, really small. Okay. So essentially what we need to do is we have this equation. C is a constant, 2.9979 times 10 to the 8th meters per second. Wavelength is 8.21 nanometers, but that's not going to cancel out with meters, so we need to convert it. There are 10 to the 9th nanometers in a meter. Okay, so I'm going to take 8.21 divided by 10 raised to the 9th. Okay, and I got 8.21 times 10 to the negative 9th. Imagine that. Okay, and this will be in meters now. This is what we're solving for. So, a little bit of algebra here. Essentially, we're solving for this, for frequency. We need this to get to the other side, so we're going to divide it over to the other side. And the units should work out. So 2.9979 times 10 to the 8th meters per second divided by 8.21 times 10 to the negative 9th meters. The meters are going to cancel out, and we'll be left with 1 over seconds, which is the units of frequency. So we're good. Okay. If you type this in, make sure you're using the EE button on your calculator, because it's going to make things difficult otherwise. So 2.9979 second EE. Mine is right there. Yours may be in a slightly different spot depending on what brand of calculator you've got. EE8, that means times 10 to the whatever exponent you have, divided by 8.21 second EE negative 9. And we get a really big number. 3.6, I guess 3 sig figs, 3.65 times 10 to the 16th inverse seconds. So what this means is, sorry, let me finish writing it here. So what this means is if you have an X-ray, which is a very, very high energy form of light, high enough to penetrate through your skin and allow doctors to see what your bones look like on the inside of your body, each wavelength is oscillating 10 to the 16th times per second. Okay, so a lot, basically. Okay. So, putting this into perspective, we need to talk a little bit about something called the electromagnetic spectrum. I'm actually going to just show you a picture that's in a textbook because I'm too lazy to redraw an entire electromagnetic spectrum. So, this is the electromagnetic spectrum. Okay, the wavelengths get bigger as you go this way. The frequencies get bigger as you go this way. It turns out that the more oscillations you get, the higher the frequency, the higher the energy is. So radio waves are very, very low energy, but very, very large wavelengths. Microwaves are higher in energy. Infrared, the entire visible spectrum, every color you've ever seen in your entire life is in this tiny little narrow range in the middle. Infrared is slightly lower in energy. Ultraviolet is higher in energy. You'll also notice that within the visible spectrum, red is the lowest energy, and as you work your way through the rainbow, purple is the highest energy. Okay. Then X-rays and then gamma rays. Okay, we don't really have anything higher than gamma rays or anything lower than radio waves, but this is every piece of light or electromagnetic radiation that you could ever envision is somewhere in this range. Okay. Not going to make a huge deal out about this, but it does help put some of these things into perspective. So when we were talking about an X-ray in that last problem, that is really, really high energy radiation. Radiation does not necessarily mean anything bad. The color yellow is a type of radiation. Microwaves are a type of radiation. But X-rays are a type of electromagnetic spectrum radiation that are really, really high energy, which is one of the reasons that doctors hide behind that lead wall when they do an X-ray, or the nurse or whoever's doing it. X-ray technician, probably. But the idea is that basically these things are pretty damaging, and you don't really want them. You don't want them hurting you. Okay. So, hopefully help put some perspective into what an X-ray actually means and what this wavelength actually means and what these frequencies actually mean. So, okay, thanks.